This example deals with using the phasor approach to calculate responses of circuits when they're excited with sinusoidal signals. Now, first thing I'm going to do is somewhat review the idea of phasor or the method of phasor. When is it valid, when can we use it, and when we can't? Now, we use phasors only to calculate the steady state response of a circuit. Now, if you remember when we were doing transient, we had a natural portion of the response and a forced portion of the response. Now, the natural portion of the response in steady state, we assume that we wait long enough for that portion to have died out. So the circuit somewhat has settled into a steady state. So in a way, what we're saying is that with phasor, we only calculate the forced part of the response, not the natural response. Now, the second thing is that we can only use phasor when the circuit has one frequency in it. In this case, in the picture you're looking at here, this circuit has only a 4 radians per second frequency. Now, many times students don't realize that it's okay to have many sources. In this case, we have 2 sources, basically 2 independent sources, one a voltage and the other one a current, but they both have the same frequency. So we don't need to use superposition. In case if we had 2 different frequencies, then we would be essentially obliged to use superposition. In other words, consider one independent source at a time. Now, of course, the signals must be sinusoidal and have been turned on for a very long time. Now, what we're going to do here is calculate VB in steady state. First thing we're going to do is convert the circuit to phasor domain. In phasor, pretty much what you have to identify is the radial frequency. Here, 4 radians per second. And anywhere that you have, of course, the resistors pretty much they stay the same. Anywhere you have a capacitor, you calculate the impedance for the capacitor as 1 over j omega c. Yeah, you'll notice that I get minus value for that impedance. A capacitor impedance being 1 over j omega c is equal to minus j divided by omega c. So it's always negative. For the inductor is simply j times omega times L, and we get J4. Now, for the 2 sources, remember phasors is defined in relation to cosine, the angle of the cosine. That's why the voltage source here, you have 8 with an angle 0 degrees. For the current source, you have to convert the sine to a cosine, and thus we pick up a minus 90 degree phase. That you can't forget. The resistors, of course, stay the same. Also, the dependent source doesn't change. We're going to look at that problem in 2 ways. First, I'm going to do a mesh because I'm going to use that example to review mesh and nodal in phasors, because the basic idea of phasors is that we can solve any circuit. In fact, we can solve circuits with 10 storage element resistors and capacitors and inductors in them. That does not really increase the level of difficulty. So the methods that we've learned, i.e. nodal, mesh, Thevenin, Norton, we can combine impedances just like we did resistances, use current and voltage division, they all work. So the idea here, I'm going to use that example to really review mesh and nodal, except I'm going to do it in a summarized way. Okay. Here, I'm starting with mesh, so I have 4 mesh currents. Now, anytime we have current source and we're dealing with mesh, this should be a flag. At this point, you should be at a point where you can look at the current source and say I4 is going to be equal to 2 at an angle minus 90 degrees. And we're going to write an equation also for the dependent current source. So first, we deal with the current source equations. We get I4 is equal to 2 with an angle of minus 90 degrees. Now, typically, I convert this to rectangular form, and that's give you minus J2. And for the dependent source, we get a relationship. We get an equation. So I4, we know I4 at this point, and I'm just going to use the value minus J2 for I4. But for the dependent source, we get an equation which says I2 minus I3 equal to 2IA. And what I do is basically write IA in terms of I1 and I2. IA is simply I1 minus I2. Stick it in there, and then collect term, and that's my second equation actually. So I need 2 more equations to complete the set. Next step, I'm going to do a KVL and Ohm's law in mesh I1. Mesh I1 is a regular mesh, no current source there, so it's simply the sum of the voltage equal to 0. Now, folks, I'm going to here in this example do both KVL and Ohm's law in one set. And at that point, I think you should be able to do that. We pretty much separate the KVL at first, and then after that Ohm's law and put them in. But it gets to that point where you should be able to do that and do it accurately every time. Pretty much what I do, I select a rotation, the rotation of the current, and I go around and say 10 I1 plus 20 times I1, because I1 is going that rotation, I2 is going against it, minus I2 equal to 8. We collect terms, and here is our third equation. Of course, our fourth equation comes in from the super mesh because we have that dependent current source that is between two meshes, I2 and I3. So we have to do a super mesh, and here I'm showing it in green, in bright green indeed, and we do basically a KVL around that big loop. That's our last equation, and you have it on the screen here. And of course, we collect terms, and we get our fourth equations. Now, what I do here, in essence, in the first equation, you see I have I4. In the second one, what I do is simply use I4, the value for I4, which is minus J2 in the equation, so that I end up with only 3 equations for a known, because I4 is basically known, so I just use it as a known value to reduce my calculation. Then we solve for all of our mesh currents, I1, I2, and I3. And from there, we can easily calculate VB from those mesh currents. VB is just basically the impedance of the inductor times I2 minus I4, because I2 is going according to the passive sign convention and I4 is going against it. Now, this is another thing you're going to have to get used to here, is that when we calculate values, remember Phasors is a method for solving circuits. So we typically have to write the response in rectangular form and in polar form, because the polar form is the one that is needed to go to the time domain form. The function in time domain is the solution, not the phasor function. So the phasor is only a way to get to that function. So the final result should usually be in the time domain if you were given a time domain function as inputs, essentially. We've done the problem using mesh. We're going to do that same problem using nodal, and of course in a very summarized way, but the steps of nodal will be reviewed. When we're dealing with nodal, of course, the choice of the reference node is always a smart one. In this case, we have one voltage source, so basically I use the negative terminal of that voltage source as a reference node, one independent voltage source. And you see that red arrow, that's basically what I'm saying is that top node at the positive sign is 8 volt. And I know it, so now it's not going to be a part of my unknown. So by now, I have only 2 unknowns, V1 and V2. So this is a significantly easier problem using nodal than using mesh. So if I were to pick, I would definitely pick nodal instead of mesh. So what I'm going to do here at this point is write 2 KCL and Ohm's law equation at V1 and V2. This is the KCL equation and Ohm's law included at node V1. How do I do this? What I do essentially, I look at node V1 and I say, I'm just going to look at the sum of the current out of it is equal to 0. So the current going onto the 10 ohm, going out onto the 10 ohm is V1 minus 8 divided by 10. The current IA is V1 divided by 20 because it's V1 minus 0. The current on the inductor is V1 minus V2 divided by J4. That way I don't have, by putting all of the current leaving a node in my mind, I can easily write an equation like that. And of course you have the current source, which gives you that minus J2. Now, when you do nodal, as I said that this problem is significantly easier using nodal than using mesh, and the reason for that statement is that that problem has only 2 nodes. But there is another part of the problem that I find a little bit difficult when we do nodal. You have to essentially deal with that equation, put it under the same denominator, and collect terms. And that has some algebraic difficulties, because here in that case, how would I deal with that? I would take that equation here, multiply the whole equation, both sides, because the 0 gives you 0 by J20, and then collect terms. But that's a few steps that you didn't have to do when you were doing the mesh. When we do that, then we get the equations that I get here with my smiley faces. And I just simply multiply it by J20. And here's our first equation, and we need one more, and we'll be able to solve for V1 and V2. Of course, if I know V1 and V2, VB is simply V1, where the plus sign is, minus V2, and the problem is solved. Second equation, KCL at node V2. And I do the same thing. You can either assume all of the current coming in is equal to 0, or assume all of the current leaving is equal to 0, and then write essentially the equations. Of course, at this point, we have also IA, and we have to write IA being V1 divided by 20 in that mix. So here I'm just showing the Ohm's law in the KCL, but we also have to write IA in terms of the node voltages. Having collected terms, and again, this is a little bit of difficulty because you have to put that previous equation in the same denominator and collect terms. And with complex values, it takes some doing. Most of you haven't worked enough with them to get the kind of comfort level that you should have. But this part of the problem, this part of the course should help you in that. We have our second equation for two unknowns. And we can solve for V1 and V2. And these are the values. And again, I'm writing them in rectangular coordinates. They also need to be written in polar coordinates for them. Of course, what I really need is VB, which is simply V1 minus V2, and then I write it in rectangular and polar form, and then at that point I can find it in the time domain form. This concludes this problem. Some last thoughts regarding use of phasors. I think this part of the course is probably very similar to what you were doing when in the first month of the course when we were learning mesh and nodal with only DC circuits, not only resistive circuits. This is very similar, not much. We don't have to deal with a differential equation of any order, even if we had several storage elements, capacitors and inductors, everything becomes algebraic. The drawback is that you end up having to know how to manipulate complex numbers. In other words, multiplication, division, addition, and subtraction of complex values should become second nature. It does help if you have a calculator that can handle those complex arithmetic, but you should be able to do them whether or not you have a calculator. And that, I think, is the problem in that part. Aside from that, we're basically doing mesh and nodal, just like we did, except instead of having a resistance value, we basically have an impedance, a complex resistance, an impedance value when we have inductors and capacitors. And of course, we have to deal with the sources. And in the case we have several frequencies, we may have to use superposition.